So in our previous lessons, we've been working with right triangles and the idea of similar right triangles to be able to find missing sides and angles based on proportions that we can write. And so we've been using those sliders to find those decimal ratios to help do that. Now, wouldn't it be nice to have them all in the same spot instead of having to use 3 different sliders? Well, there is a combination of all of those things. Mathematicians built for many years the trigonometric ratios that we've been studying, the opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent, and compiled them all into a table of values for all of the angle measurements possible for whole degree measurements for 0 to 90 degrees. And so they're all compiled here on this chart. You have the digital link on your class kick, and when we are in person, you'll get a hard copy of this as well. And so what we want to do is take a moment to think about, well, how this table was compiled, and are there any things that you notice about patterns that are perhaps within the table? Okay, so this table here is on your slide 3 for your class kick, and let's give you a few minutes to examine some of those ratios, right? So we were looking at the opposite over the hypotenuse, the adjacent over the hypotenuse, and the opposite over adjacent. We'd like you to take a couple minutes to look at the following. Take a look at each column individually and the decimal ratio values that happen as the angle size gets bigger for the opposite over hypotenuse column, and tell us why you think that happens. And you can use the Desmos link below to help you think about that. You also can go back to the table for that one. Then, once you're done with the opposite of hypotenuse, take a look at the adjacent over hypotenuse column, and again, examine that as well and write about what you see. And last but not least, we have our third column, the opposite over adjacent. Again, look at those ratios in the columns and write about any patterns that exist. Okay, so we'll give you a couple minutes to do that. I'll go back here to the table so you can take a look at that. So in looking at the opposite over the hypotenuse column, a couple of things. As the angle size gets bigger, those decimal ratios go from about 0 to 1 in value, okay? When we're looking at the adjacent over your hypotenuse column, those actually decrease. They went from about 1 to 0 in value. And the last column, you've got your opposite over adjacent, and this one was a little bit different than the other two. The ratios went from 0 to about 58, and then all of a sudden when you got to 90 degrees, it was undefined. And so if we think about kind of why is that happening, when you're talking about standing at your angle, the opposite over your hypotenuse, right, as the angle got bigger, as your angle gets bigger, that opposite side length is getting longer and getting closer and closer to that value of 1, right? So that's why those ratios are behaving in that manner, right? That opposite side there in green, again, longer and longer as that angle goes up and gives you closer to that value of 1. Now, when we were looking at the adjacent over the hypotenuse, as the angle increases, your adjacent side is here, watch what happens to it. It gets smaller and smaller and smaller, getting closer and closer to that value of 0, okay? So again, we're going to watch as the angle increases, that adjacent side here, right, is getting smaller and smaller and smaller. Now for our third ratio, the opposite over the adjacent, okay? So this is where we are right now. We're going to watch these sides, okay, in our ratio here. As the angle gets bigger, the ratio is getting larger and larger and larger accordingly, Okay, so we're looking at just those lengths of the triangles. We've got the visual to match with your decimal ratios. So let's take a look at a couple of examples here. So I gave you a template for a right triangle, and we want to look at the ratio of the opposite over the hypotenuse for a 30-degree angle and an adjacent over hypotenuse for a 60-degree angle. So using your table, we can write what those ratios are going to be based on the given. So for the first one, I can look up the opposite over hypotenuse column, go down to 30 degrees, and I can get my answer there. The other one, I can go adjacent over hypotenuse column, go down to where 60 degrees is, and get that decimal ratio there. And so if we think about what those decimal ratios are, they end up being the same. The question, well, why is that? So we have a 30, 60, 90 triangle, right? So if you're standing at the 30 degrees, here's your opposite, here's your hypotenuse, right? And if you're standing at the 60 degrees, here's your adjacent, here's your hypotenuse. Well, guess what? We're talking about the same side lengths to use for those ratios, even though we're at different reference angles, okay? But it's still the same special triangle, right? 30, 60, 90, two same sides. That's why those ratios are being equal. So we're going to use this item kind of thinking about finding ways to get some measurements. And so if we continue on using our table to help us, you've got your table tab open from your previous slide. Let's see what we can do with these. What we want to do is find the measurement for angle A to the nearest degree. So we're going to look to see what ratio is being used, okay? We're going to find that decimal ratio to it, or as close to it as possible, and we'll look over to the left to find that value. So for example, we're doing the opposite over hypotenuse, and we're going to go down in the table and look for 0.1564. So what I'm doing is I'm looking at my opposite over hypotenuse, and I'm going to go down in my table and look for that 1.1564, see if I can get an exact match or something close to it. Well, I see it's right here. What's the angle it corresponds to? That would be 9 degrees. So I'm going to have 9 degrees for my angle measurement for A. Let's try another one together. Let's see if we can do the adjacent over hypotenuse for angle A. That gives us a ratio of 0.6157. Okay, so remember, we're going to go to the table, look in our column for adjacent over hypotenuse, go down until we see this ratio or something close to that, and it will tell us the angle. So again, we'll go to our adjacent over hypotenuse in the table. We're going to look down to 0.6157. And I'm going to have to go to my other column here, 0.6157. Up here it is, I see it. And that goes with our angle measurement of 52 degrees. So I'd like you guys to try answering the remaining questions using the same pattern in your table that we've just done for these two, and then we'll check your results. So if things are going well in your table, again, we went to the opposite over adjacent column, look down to find this match or something as close to it as possible without going over, and we have a measurement of 71 degrees. Okay, we went to then opposite over hypotenuse column, look down to find this ratio for an exact match or something close to that to find our angle measurement. That's 64 degrees. So again, what we're doing here is similar to what we're doing with the slider. Instead of having to adjust it, we're just looking in the table to see where our match is. Our next one, adjacent over hypotenuse for our ratio of 0.8910, gave us a measurement of 27 degrees. And opposite over adjacent with the ratio 0.8098 gave us a measurement of 39 degrees. So let's try doing some more based on these givens. Here we have the ratio and we have the angle. Could we find the decimal ratio that goes with it? So we could do some calculations. So again, we're going to look at here, and that tells us what column to use. This is the angle measurement, and then we can write the decimal ratio that goes with it. So we're going to go to opposite over hypotenuse of 35 degrees and see what our decimal ratio is. So again, here's the column we need, opposite over hypotenuse. We're going to go down to 35 degrees, and we can see our ratio is right here, 0.5736. So that would be our answer for that question. Our next one said, well, let's do opposite over adjacent, and we'll do 75 degrees. Okay, so we're going to go to our table and find our column, opposite over adjacent, and go down to 75 degrees to get our decimal ratio. So again, opposite over adjacent, I'm looking for 75 degrees. That's here. Opposite over adjacent, I'm going to write 3.7321. All right, let's see if you can do the next one. We're going to have you do a quick check. Adjacent over hypotenuse of 47 degrees with your table. Adjacent over hypotenuse for 47 degrees. So again, we find our column adjacent over hypotenuse. We're going to go down to the degree measure that they want. Oh, it's not in that first side, so we're going to go to our second side, adjacent over hypotenuse, 47 degrees. That's 0.6820. We've done 3 together. Let's give you a little bit of time to try the other 3 in your table just to make sure you're comfortable when given the ratio and the angle. The ratio as in definition of opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent, and the angle measurement. Can you find the decimal side ratio related to that? All right, if things went well and you went in your column for opposite over adjacent for 25 degrees, your decimal side ratio is 0.4663. If you went to your adjacent over hypotenuse column for 82 degrees, your decimal ratio is, for the side, 0.1392. And again, if you went to your ratio column for opposite over hypotenuse for 62 degrees, your decimal side ratio is 0.8829. Now that we're comfortable using the table to find the decimal side ratio needed for the given angle measurement, and given the decimal side ratio, finding the angle measurement, let's put this into practice and solve for some missing sides and angles of right triangles. So we look at our first problem here, okay, we want to always ask ourselves, where are we standing and what ratio would we need? Well, we know that we should be standing at the acute angle, never at the right angle. So we're standing here at 63 degrees, and x would be our adjacent side, and 12.8 is the hypotenuse. So I focused in the part of the table with my angle of 63 degrees, and if I'm using the adjacent and hypotenuse, I'm going to have to look at this column here for the pieces. I know I have to have x over 12.8 is equal to, and then I'm going to get my ratio from my table. Well, again, adjacent over hypotenuse, 63 degrees, I've got to use this when I write my proportion. So my proportion should be x over 12.8 is equal to 0.4540 over 1. Now, you guys are masters at when you have your proportions using your means extremes, your cross products to solve for x, or some of you notice that x is being divided by 12.8, so you just multiplied both sides of your proportion by 12.8, and you'll still get the same answer. And if we round to 2 decimal places, it's going to be about 5.81 in length. Remember, when we talk about rounding to the hundredths place, we look at the 3rd decimal place, the thousands. Based on that value, if it's 5 or higher, you have to round up. If not, you leave it as is. All right, let's take a look at another one. I see I've got this right triangle, and I'd have to be standing at the 71-degree angle, so I'm going to focus on that part of my table. I also see this length of x that's opposite of where I'm at, and 32 is next to, adjacent to where I'm at. So I'm going to have to work with that opposite over adjacent part of my triangle. So again, if I look at the 71 degrees for opposite over adjacent, I see I need that 2.9042 as the other piece of my proportion. Again, you can use your means extremes to help you solve it. In this case, x is also being divided by 32, so you can multiply each side by 32 to help you get your answer. And if for rounding to the nearest hundredth, 2 decimal places, we're talking about 92.93 units in length. Again, if you want to check and make sure you're on target, anytime you're solving for a variable, you can take that value, put it in place of where it is in your equation, and just make sure both sides are equal. So if I take 92.93 and divide it by 32, I should get back approximately 2.9042. All right, let's give you a minute to try setting up this problem based on your givens. Think about where you're standing, what ratio do you need, and what proportion can you write. So here we're standing at the 27-degree angle. Our opposite side is 18, our hypotenuse is x. So I'm looking at opposite over hypotenuse. I'm going to go to that column, focus on the 27 degrees, and this is our decimal ratio I need, 0.4540. So I can write my proportion and then think about solving. So again, we can do our means extremes, our cross products, right, to solve for x. I'm taking x times 0.4540 equal to 18 times 1. I know 18 times 1 is 18, but notice how x is still not alone yet. It's got this multiplier, so to undo that, we have to divide each side by that decimal ratio. So if I do my calculation for x, I've got 18 divided by 0.4540. I'm talking about having a hypotenuse with a length of 39.65. All right, so let's try this one here. Let's see if we could write a proportion to help us solve. So where are you standing and how are those sides related to where you're at? We are standing at the angle for x. We've got our hypotenuse of 63 because the right angles always point to the hypotenuse. And we've got 12.8 as the adjacent sides. We are looking at the ratio of adjacent compared to the hypotenuse. So here, since we have the two side lengths, we'll have the decimal ratio, which is good because we need that to find the angle measurement. So if I write 12.8 divided by 63, this is the decimal ratio I have to find in my adjacent over hypotenuse column. So I'm looking for that exact value or something close to it without going over to find my angle measurement. So as you guys are looking, you should stumble across it being about 78 degrees. And remember, the table goes from to 0 about 45 on one side and then 46 to 90 on the other. So if you don't see it in one half of the table, make sure you look in the other half to answer your question. So again, when you're looking for the angle measurement, you're going to get the decimal ratio from the sides. That's what you're looking to match to find the angle measurement. Let's have you try one more. Based on your triangle here, can you find the angle measurement? We know we're standing at the angle for x. 14.7 is opposite of where we are, and 18.9 is adjacent to where we are. So we're looking at using the ratio of opposite over adjacent. And since we have both side lengths, we'll know the decimal ratio to use to help us find the angle measurement. So in that opposite over adjacent column, we're going to look for the decimal ratio that is as close to a match of this as possible, and that will give us the angle measurement that we need. So that's bringing us to about 38 degrees. Now it's going to be your turn to practice finding missing sides and angle measurements. Same idea as before, but now we have the table to use versus the sliders to calculate those missing pieces, okay? So everything is here. You've got the tables that you could click on here if you don't have that link open. This is just a scientific calculator that you can use to do your calculations. Just remember you're rounding side lengths to the nearest tenth for the answers for these and angles to the nearest degrees. Happy practicing.